Welcome everyone to our FBAN webinar today. I'd like to put in an apology from Mike Wouters from the Predictive Services Group, who would normally be presenting to you in my place, and also Darcy Pryor, who was leading the AQFX project team over the last couple of years. Before I hand over to our presenters, I'd like to acknowledge that I am on Wurundjeri country and pay my respect to the elders past, present and future, and also acknowledge any traditional owners that are out there today, including Maori people who may be tuning in from New Zealand. Just like to introduce Dr. Fabian Ryson from CSIRO, who's going to lead off the presentation here this afternoon. Thanks, Fabian.
Thank you, Deb, and thank you everyone for joining and giving us the opportunity to present here. So I will start off with the presentation and then hand over to Karen McTaggart to finish the presentation. So today I'm going to mainly talk about the data inputs that go into our air quality forecasting system, AQFX. So I would also start by acknowledging the traditional owners of the land, sea and waters of the area that we live and work on across Australia. Just knowing too that over the course of the study that I'm presenting to today, we have been doing some field work across many areas of Australia. We would like to acknowledge their continuing connection to their culture and pay our respects to elders past and present. So today I'm going to present to you from the land of the Wurundjeri people of the Kulin Nation. So starting off, it's just give you a brief overview how the air pollution forecasts are generated for the AQFX system. So we're using the Bureau of Meteorology's weather forecast to determine the smoke dispersion, where the smoke plume is going to be going. And underpinning that one are all the national emissions. So what we're looking at is not just the smoke emissions, but we also want to know all the background emissions from anthropogenic sources, so including all the urban emissions, as well as all the dust emissions and sea salt emissions. So all that data then gets put into our chemical transport model to then determine the ground-based concentrations of fine particulate matter, as well as the fraction of that fine particulate matter that's due to smoke. So today, I'm really going to focus on the central part, on the emissions, and working through how we derive the emissions currently in our model and where we're planning to go with our national prototype system that we're currently working on. So in our system, our smoke emissions, we use a bottom-up approach to derive how much gets put into the atmosphere. So on the top, you see the equation. So that one is the emissions. Fluxes that we derive is a product of how much area is going to be burned, how much fuel is available on that area, and of that available fuel, how much is going to be consumed during the fire and thereby being emitted in terms of smoke. To look at specific pollutants, we develop emission factors. So those ones determine how much of each pollutant is emitted per amount of fuel that we're burning. So I'm just going to work through each aspect to indicate what we currently have in the system. So starting off with the fuel load. So in terms of the smoke emissions, we're interested at both the fine fuel load, but also the coarse woody debris, because the latter one are consumed mainly by smouldering combustion, and they can have quite significant impacts on local and regional air quality. So we know that the smoke plumes often don't disperse as well, but they can cause some localized high particle concentrations. So currently what we have in our system is for Victoria, as part of the development of the AQFX system in 2016, we have upgraded the fuel load data sets using empirical fuel load information. And then for the rest of Australia at the moment, we use the semi-empirical model called VAS, the Vegetation and Soil Carbon Transfer Model. And that one at the moment, we've seen that there's quite a coarse resolution of the fuel load data sets that we derive from the VAS model. And as you can see on the picture on the right-hand side, we have some challenges with some of the areas close to the coast where we have zero fuel load. This means that if we have any fires burning in that area, we don't recognize any fuel, which means that we don't derive any emissions. So in terms of going forward for the national approach, for the fine fuel, we would like to adapt the fuel maps that are part of the Australian Fire Danger Rating System project. And for the coarse woody debris, we're moving to the process-based carbon cycle model BIOS-2. The next step is then to know, once we know what fuel is available, how much of that fuel is actually going to be consumed, either during the bushfires or the planned burn operations. So we're using the burning efficiency equation developed by the National Greenhouse Gas Inventory, which is a product of the fire patchiness and the combustion factor. So currently what we're looking in the model, we have different strata that we're interested that we have simplified. So we're looking at the surface fuel, so which ones includes both the fine fuel and the coarse fuel. Then we would have bark, the grass, and the elevated strata. So for bushfires, the way we're looking at what of the strata is going to be developed, we're looking at sort of the curing and drought factor, and then also depending on whether elevated fuel is going to be consumed, that's going to be determined by the fire behavior, so the flame height intensity. For planned burns also, there we're assuming that most of the surface fuel is only going to be burning. And in terms of the burning efficiency, we relied on some of the studies that were conducted in Australia. So one is a report by Stephen Roxburgh et al. That was published in 2015 that looks at the burning efficiency for fine fuel and coarse woody debris based on whether it's a planned burn or a bushfire. And we also sort of compared that one with some of the data that came out of a paper by Jan Hollis, looking at the coarse woody debris fuel consumption. So we can see that for the larger classes of coarse fuel, which are larger than 2.5 centimeters, we have about a 44–45% fuel consumption. So that data then goes into the system to derive smoke emissions. So the next plan is then how to derive the emission factors. So when we developed the AQFX system, we ran a number of laboratory experiments in the CSIRO Pyrotron, as well as doing some field measurements. So for the field measurements, we use a portable backpack sampler that you can see in the picture in the middle, where we're collecting both gaseous components in a Tedlar bag, which we analyze then in our laboratories for carbon monoxide, carbon dioxide, and methane. And we're also collecting particle samples onto filter for later analysis. During the burns in 2015, we also had a team from the University of Wollongong who used an open pass FTIR to derive some of the emission factor for the gaseous components. So I'm just showing some of the results, focusing on sort of the emissions from the flaming and smouldering combustions. So using our backpack sampler, we were able to focus specifically on the flaming combustion and distinguish it from the smouldering combustion of the coarse woody debris. So as you can see on the graph on the left-hand side, on the bottom, I show the methane emission factor, carbon monoxide, carbon dioxide, and then the total suspended particles and the fraction of fine particles, PM2.5. So you can see that for the gaseous components, really the flaming combustion shown here in red, we can see really low emissions for methane and carbon monoxide and higher emissions for carbon dioxide. So the more efficient our burning is, the more of the oxidized compounds are going to be emitted. Whereas for the smouldering combustions, we see the inverse, having higher emissions of methane and carbon monoxide. For particles, what we did is that there's various processes that go coarse woody debris is undergoing during combustion. So we looked at sort of the initial ones where we have the pyrolysis, where we have the emission of gases, which are not very volatile and condense onto particles, which we see as the white smoke on the picture on the right. So we have quite high particle emissions to the pyrolysis stages. And once we have sort of the char forming, what would happen too, there's more reaction, oxidation reaction occurring on the char, and that's a surface reaction, where we often can see that we have higher emissions of the gaseous components, but low particle emissions, especially during gasification, which is sort of the char, which is the surface oxidation at high temperatures above 600 degrees. We can see that the particle emissions are really low. We also can see that there's a fair bit of variability in the particle emissions as well. So it's going to be quite challenging to determine like what other factors are actually going to drive the particle emissions during the combustion of this coarse woody debris. So we're trying to look at various factors. So the obvious one that's often used in the literature is the modified combustion efficiency. So that one really indicates how efficiently your fuel is combusting. And there it's really good to distinguish usually between the flaming combustion and the smouldering combustion. But we can see even at the lower MCE going into smouldering and residual smouldering, we can see quite a large variability. And we also seen that one in the literature. I've shown a few regression lines that were determined from literature data, and we can see there's quite a variability in terms of the emission factors derived as a function of MCE. So it sort of indicates to success that it might not be the best predictor to assess the particle emissions. What I've also done is looking to simplify it a bit and put the emission factors into 3 different components. So we have the initial high intense flaming combustion, which usually lasts it's sort of a shorter time frame. Then we put into the model the smouldering combustion, which is probably going on over the next few hours during a bushfire or plant burn. And then the residual smouldering combustion is really when you have the larger logs still combusting for hours or days after a fire or plant burn has come through. So if you're looking at that one, we can still see that there's not a big distinction between in terms of the particle emission factors between the smouldering and residual smouldering combustion, but again, quite a large variability. So what we tried then is to understand whether there's other factors that can explain this variability a bit better. So we looked at combustion temperature. So what we've done in a recent project looking at smouldering combustion of coarse woody debris, we used a thermal imaging camera to capture an average, capture the combustion temperature of the smouldering logs. And as you can see, it looks like it's quite a good relationship. So as the temperatures go down, we actually have particle emissions going up. So the next big component of that going to drive the emissions, of course, to understand how much of the area is burning. And Karen is going to go into more details about what's currently in the system for Victoria. So at the moment, we're having 2 different systems where we use the PHEONIX fire spread model for both the bushfires and plant burns to derive how much of the area is going to be burning. In terms of the national prototype system, what we currently have in the system that we're using actually the hotspot data from the satellite VIAs and MODIS. And so what we looking at all the hotspot data in the area, and we develop sort of a cluster around these hotspots, and that area then we assume that's the area that is burning, and that's the area that we're then deriving the emissions from. So there's definitely uncertainties based on that model, because we know that the satellites overpasses, there's about 4 a day that we can see. And there also might be that we're missing out on some of the hotspot data because too much cloud coverage or too much smoke. So our plan forward is really to use a national tiered approach in the future. So you can see on the diagram where we started off is looking at our hotspot data with the cluster analysis, moving into hotspot data that we're identifying and then forecasting the fire spread using Spark. So with the current system, we assume there's a persistence the hotspots. We got the hotspots data, and then we assume there's a persistent fire during that time period. Whereas with the hotspot data and forecasted fire spread, we're looking at what's currently fire activity frontline, and then we use a fire spread model to go forward to sort of see how that fire is going to spread. Where we would like really to get to is using fire agency data, either getting the ignition details and then forecasting the fire spread using Spark, or using fire shapefiles provided by the different fire and land management agencies across Australia. So in terms of the fuel load too, recently come across one of video from a PhD student in University of Tasmania to sort of understand how we could actually better capture the coarse fuel load for determining the emissions from the coarse woody debris. So this one really shows you sort of photogrammetry where we can determine sort of how much of an area we could see sort of coarse woody debris, and use that one sort of from a limited grid sampling to maybe move to a larger scale. So we're currently looking into how we could adapt that one to better refine the coarse fuel load in certain areas. In terms of going forward too, we know that smouldering combustion is probably one of our larger uncertainties in our model. And so we're looking at different ways how we can improve the inputs to have more robust forecasting. So as I mentioned in the previous slide, we know there's quite a good relationship between combustion temperature and particle emission factors. So what we could do too is then develop a better distribution of combustion temperatures from smouldering coarse woody debris over a larger area to get us an understanding on a distribution on what temperature most of the coarse woody debris might be burning at, and then derive from that one our emission factors and hence our emission fluxes. The other way to refine the forecast from the smouldering coarse woody debris is to refine the emissions based on observational data, either on the ground or from drones, and with inverse modeling. So by that I mean that we have a network of monitors, either around the planned burn operations or mounted on a drone. And then we use that information then to do the inverse modeling and infer the emissions. Another approach too, we know that quite a large uncertainties is due to the area burned and the fuel that is actually consumed. So we could use a top-down approach using estimating the emissions with satellite observations of fire radiative power. So using that approach, we wouldn't need to know the area burned and the fuel consumption. So we would have an emission coefficient which is independent of fuel type. And then you would do the integration of the fire radiative power over certain areas, as we can see from the satellite. So there's definitely some advantage of using this method, but also some disadvantages. In terms of the disadvantages, we know that some satellite have limited passes, so it's limited by a temporal scale. We also know that during cloud coverage and dense smoke, we might not be able to get the information that we need from the satellite data. And also it's quite a weak signature for the smouldering combustion. So this might be a really good approach to look into estimating the flaming combustion emissions. But for the smouldering combustions, we might be a bit more limited. So going forward, we think that a combination of the different approaches will enable us to give us the most robust short-term smoke forecasting. So linking all the information that I presented in the webinar today. So looking at sort of our bottom-up approach, using data from the fire and land management agencies in each state and territory, and then complement that one with some of further on the ground observation, either via drone images to improve the fuel load information, and then combining that one with the satellite information as well. The last thing I would like to mention too is that often what we've heard is how do we deal with bushfires where we want to have a high temporal resolutions and the plant burns where we want to have a really high spatial resolution. So our plan going forward is to, as part of funding through the Australian Climate Services, is to develop a rapid update cycle forecast, which provides information on smoke forecast on an hourly time frame. So for bushfires, for example, we would use satellite data from the Japanese satellite Himawari and deriving the hotspot data, using the hotspot data from that, which are provided at a 10-minute updates. And then drive using the hotspot data to drive then so fire spread using the Spark model, and then derives the emissions on an hourly time frame. For the plant burn operation, so at the moment, our current system is 3-kilometer resolution for Victoria, Tasmania domain, but on a national scale, we have a 9-kilometer resolution. So you can see the difference on this video. On the left-hand side is 3 kilometers, and the right-hand side is, oops, go back. Right-hand side is the 9-kilometer grid. So you can see that there's definitely more definitions, the more finer resolution, spatial resolutions we can get. So it's really working through as well with the rapid update cycle to have a finer resolution of 1 kilometer, so we can better target the plant burn operations and the smoke dispersions from those plant burns. Okay, and now I'm going to hand over to Karen to go over information for DELP. Thank you.
Thank you, Fabian. My name is Karen McTaggart. I work for the Victorian Department of Environment, Land, Water and Planning as a Smoke Management Project Officer. I'm involved in this project as an end user to support the ongoing development of smoke forecasting models and to provide expertise and to facilitate the exchange of knowledge between the end users and the project team. So as an end user with the smoke forecasters, Fabian just presented the complexity of the model with all of the things considered. One of the easiest things that we can actually do to get better forecasts is to improve the input data of where the fires or planned burns are. So improving both the quality as well as the accuracy of the information. So the first thing I'm going to talk about is the planned burn data inputs. So at the moment, Victoria are the only one who are putting in automatic inputs to get planned burn forecasts. And with these forecasts, the uses a fire behavior simulator, PHEONIX Fireflux, which is similar to PHEONIX Rapid Fire, but with modifications for both a planned burn simulator as well as a fire simulator. I've included a reference at the bottom of the slide that has all the further details, including the specific programming that is used in this if you're interested in learning more about the PHEONIX Fireflux. From a fire agency point of view, though, we export a shapefile of planned burns with a set of attributes, and this is sent to the Bureau of Meteorology to run through Fireflux and combine with the weather inputs, and then run through the emission model to get the smoke forecast. In Victoria, these are exported twice daily from our scheduling system using an automatic process. Currently, planned burn forecasts only run in Victoria, as I was saying before, but in the future, we intend to add other state planned burns into the system. So there is actually a need for having consistent methodology, including consistent attributes, so that we can understand each state's data, as the smoke obviously goes across border lines. So in Victoria, we need to understand what New South Wales planned burn inputs are, so we can interpret those for their effects in Victoria. So the attributes that are currently include a range of burn ID information. I haven't included this in the the table. This information is used mainly to understand what the burn is and understand some of the inputs, such as the size of the burn and when the ignition time was, which is also included in the table though. So currently we're running 2 planned burn forecasts, one the day before, which includes all the planned burns we think we might ignite the next day, and then one in the morning on the day that we plan to ignite. And included in these is, in the output, is in a number of days. So in the table I've only shown day 0 activity, which is a current day, and day 1 activity, but we also have up to 5 or 6 days of data in there, so that if we change the status of a burn, then the forecast will be run based on that status. So the main things included with that shapefile is the size of the burn, as well as the target range coverage that we are aiming for. So one of the assumptions with this model is assuming that that target is going to be achieved. So if there's a target of 60 to 80% coverage, the model assumes that 80% coverage will be achieved. And with PHEONIX Fireflux, it runs the software burns from the driest areas, so the most available fuel, to the wettest areas until this coverage objective is reached. So if a burn is 200 hectares in size, but on day 1 only 100 hectares is planning to be burnt on that particular day, the model will actually only burn 80% of that, so 80 hectares for day 1. And then in the second day, patrol is put in there so that we can still have the smouldering emissions for those following days. So it simulates a single day burn, assuming that a multi-day burn can be partitioned into different blocks for different days. With our system over the last couple of years, we have made some large improvements to what we can include and export, but there are still some burns, in particular extremely large burns, that may not get divided into those blocks. So increasing the accuracy and making sure that we're only putting in that particular block that is intended to be burned for that day is probably the easiest way to actually increase the accuracy and the usefulness of the smoke forecast. We've also recently included in our scheduling system a spot where the burn controller can put the intended ignition time. At the moment, all our forecasts are running with an ignition time at 11 o'clock, which we realize is often unrealistic, especially in situations where we're waiting for those fuels to dry out. The other thing as well is they're all set for a set period of ignition duration. So we're looking for in the future that we'll be able to put an estimated time of ignition to be able to change how long that is run. So the better information we can get will produce the better forecasts, but it's also important to actually understand the assumptions that are made, as the forecasts will be run in the morning and things will change during the day. So by using this information, the assumptions that are put in, the inputs that are put in, knowledge about the weather conditions and the fuel conditions, we can then interpret the forecast and make assumptions so that if we do decide to burn a few hours later, we can then use the current forecast that we have, say, for example, starting at 1100 hours, and make a judgment based on the weather as what we think the forecast would look like if we moved the ignition times by a few hours. So I'm now going to talk about the agency data that is put into fires. So next slide, please. So currently with the fire agency data that Victorian submitted, it's similar to the bushfires in that we're using PHEONIX Fireflux, but with a bushfire simulator with modifications. So a shapefile with ignition details are taken from our emergency fire data feeds and run through the system. A fire simulation starts from a number of ignition events with a time and a location. PHEONIX then simulates the likely progress of the fire. At the end of a time step, the area burnt is identified as a polygon, and the total amount of fuel is then that is consumed is then calculated and added to the emission models to produce the smoke forecasts. So at the moment, this is where we're at with the input data that we're putting in, along with the fire hotspots that Fabian was talking about. In the future, we have the possibility about adding other information, and one in particular is the ability to add backburns, and the thoughts at this stage are to add that with a similar method to what we would do with the planned burns, is to put in the polygon and have that being ignited at a particular time for a certain number of hours at a lower fire behavior than you would expect with the fire emissions. Another thing we want to be able to do is actually add manual validated fire behavior predictions. One of the key important things about this, as everybody knows who uses an automatic fire behavior simulator, is one of the first things that comes up is the first ignition call where the fire was put in is often a location and that hasn't been verified. So improving the actual ignition location manually would be extremely important in actually getting very accurate forecasts, as well as other things such as local knowledge about fuel load availability, fire suppression success or availability to get quick fire suppression and backburn. So by having that information and making manual predictions and putting those into Phoenix, we'll get a more accurate smoke forecast. So there's several ways we're looking at testing at doing this. So we have the option to put in the hourly polygons that each represent each of the hourly time steps. Or alternatively, we could put in a fire predicted active area at particular time steps, such as once a day, and then let Phoenix run that as it currently is now. And then that would probably be a preferred way to get a quick and easy forecast with accuracies improved, such as the location, or also out to several days based on local known assumptions about the fire. Another thing as well that we are trying to do is include other sources of smoke, including agricultural burns. So at the moment, if the burn is large enough and hot enough, it will be picked up at the hotspots and included, but often they might not be, and that can add a lot of background smoke, especially during planned burn season. And another thing as well that is really important to do is a lot of the smoke forecasts, to actually interpret, we need to understand what is actually happening, especially when it comes to interpreting other states and national incidents. So including the agency data feeds of incidents and timely information about when the fire starts from when it's being ignited to when it's going to when the fire is being put out is important in understanding, especially when a smoke forecast might not include all the suppression. It might be adding more smoke to the atmosphere when in fact our agency is actually going to put those fires out. So having a good understanding of those alongside the system is important in interpreting the forecasts. That pretty much covers all the information that I have on the agency fire data. So if there is anybody in any of the other states that's really keen to get their forecasts in with manual or validated fire behavior, they can feel free to contact me to discuss, and we can look at doing that. So thank you everybody for your time in coming today, and I'll hand back to Deb.
Better if I'm not muted. Thanks for that, Fabian and Karen. Some really interesting stuff coming in, that smoke modelling. I'll just see if we've got any questions from the audience. We don't yet, but I have lots. So first of all, a lot of that modelling you were showing was based in like sort of woodland, temperate eucalypt forest. Are you looking at other fuel types for that as well? grass, Minifex, some of the other models that are in the Australian fire danger rating system?
Yes, we will be. So at the moment, the way we're going to capture it too, that we have specific emission factors depending on which fuel type we're going to burn. So those are the work that we have been doing was in, of course, in the forested areas, but we're also going to look at some of the emission factors even that were developed through some of our previous work up in the savanna grasslands. So we're using lots of that information. Anything that's burning up in Northern Territory, if that's that fuel type, we're using those emission factors, and the same goes for grasslands as well. So we're hoping to update our emission factors and then having that one linked with the fuel maps to then drive whatever is burning, those as emissions that we're going to use.
Yeah. Just on the smoke predictions, are you just using wind speed and direction, or are you looking at sort of mixing and inversions as well to say, well, this valley is likely to fill up with smoke, or it's going to go CB and just go everywhere? So
yeah, it's sort of more the complexity as well. So it has the whole boundary layer conditions in there. So the way the chemical transport model works, it's that it looks at different layers. So even if the smoke gets lofted quite high in the atmosphere and then might come back at a lower layer, that one will be captured as well. So we definitely look at the various layers. We also going to have, what I didn't mention today, is working through a more dynamic plume height as well. So linking it to the fire intensity so that we know to how high the plume height going to go and then how it's going to disperse. So there's a bit more complexity just than the wind speed and the wind direction.
Yeah. And Karen, have you been using this for real-time predictions for smoke for like health warnings in going fires or just in prescribed burning so far?
No, it definitely has been used in going fires over the seasons. And my job role, I actually haven't been around to witness that, but I know in past seasons it has been. And I know the EPA use AQFX forecasts and are constantly talking in the State Control Centre to the agencies to just confirm that what they're seeing is what would be expected before those health warnings are going out.
Yeah. I know after the 1920 fires, you know, there was a lot of media around 400 deaths from smoke. So you'd be hoping most people have evacuated and not in the line of the smoke, but in the case where they are, that's really great that we're able to use that for health forecasting as well. So I've got a message here on the chat. So from Damien, does the emissions predictor and Fireflux have the ability to interpret a temporal graduated polygon as an ignition pattern that is more representative of operational lighting patterns?
That is not an easy question to answer. Simply, basically, yes, it definitely can. And that's something that we want to work with the fire agencies about, how they're actually submitting the data to be able to work for that. One of the things, though, with planned burning that is important to consider is that a lot of planned burns are small and therefore the smoke effects are small, whereas the resolution of the system at a 3 kilometre resolution, we're looking more, well, it was developed more to look at cumulative smoke effects rather than the close nearby smoke effects. So sometimes that ignition pattern isn't probably the most important driving thing for that particular planned burn, more so just making sure that the actual size and the location of where the ignition is happening. So the important thing is if you've got a 50 hectare burn, for example, but you're only burning 100 hectares of that, but that's located in a southwest corner where the fuel is quite different than over the block, that only that one small corner is actually submitted for that smoke forecast for that day. And that's what we're working on currently, is making sure that where ignition is happening for that day is represented in the input data. So that's probably the easiest way at this stage, but it depends on what data is known and how likely as well that is actually, the planning is actually going to represent the outcome. I also know we're looking at the differences between if you're edge lighting rather than if you're doing aerial burning, and the type of fire that is resulting from aerial burning compared to just on ground on foot.
Great. A question from Sean. the designer of the Fireflux system. Oh, it's more of a comment, I would say. Great to see it being used. Just wondering if you've been investigating the new fuel load spatial model that has been developed recently by the University of Melbourne.
Thanks, Sean, for that question. You probably could have presented your work a lot better than I did. Maybe, Fabian, have you looked into that? I don't know that we have yet, have we?
No. So at the moment, what we're planning to look into is more looking at sort of the spark fire model, how we can implement that one into the EQFX system. But yeah, we haven't really spent most of our time at the moment was really spent most on the emission factor development. And yeah, going back into sort of how we can better do the fuel modeling as well.
In another life, I'm working on Spark, so it's good to see that you're integrating into that as well. So.
Yeah, it's also important to note as we move forward, we're looking to make sure that it's consistent with the AFDRS outputs, so that yeah, we're looking at making sure that the input data is the same.
Yeah. Question from Kelsey. In the future, do you see this being able to be interpreted and utilised for community engagement about planned burns with members that are concerned for bees and vineyards, so to settle their nerves about smoke on the day?
Yes, it currently is being used for that. I've actually got another project that we're running at the moment looking at smoke, the potential for smoke taint. So we are currently in the process of doing that. The difficulty there with some of the community impacts is that it's not necessarily just the PM 2.5 concentration that we use for the health. So the research that we're looking at is how we can then take the forecast information that we've just presented and then use that to transfer that into predicted smoke load, which will have the effect on the smoke taint. So there's a bit of work to be done with that, and we're hoping that over the next plane burns season we can get out there and validate some of the work. As well, of course, the important thing is having sensors out there. So that's also another thing for vignerons, is that we might have the forecast, but we might not know what actually eventuates exactly at that particular vineyard location, especially when there are vineyards out there that we don't know that are there. So we might not record at that particular time. So there's an opportunity for vignerons to actually buy their own smoke sensors so that they can get a better idea of whether they've been impacted or not.
Great. I suppose, yeah, you think about smoke holistically as just smoke, but there's probably, you know, gaseous smoke and particulate smoke, and they all have different effects on people. So yeah, it'd be great to be able to break down your smoke forecast into those particular levels rather than just smoke. Another question for you. So this has really been a prototype project with, I think it's DELP, CSIRO, the Bureau, and I think the Rural Fire Service in New South Wales has been involved as well. How do you see it being rolled out nationally?
Do you want me to answer that, Fabian, or I'll let you answer that one?
If you're happy to answer it, Karen, yep, you can go ahead.
Yeah, well, that's a really good question because it's really exciting at the moment. So the prototype AQVX is being rolled out nationally currently. So over the different jurisdictions, we've actually in the process, we've delivered some training, we'll be delivering more training. And at this stage, the important thing with that is actually getting user feedback. So making sure we've got the science, we've got expert scientists who know how to work the emission models. The key thing is then getting that out in the useful format for the end user to be able to make sure that they're using that to make the correct decisions and being able to use that for proper management. So at the moment, there's a survey open for AQVX to feed that information back and provide comments as to what the system is missing or needs to be altered for the best use.
Probably worth noting that AQFX is the air quality forecasting system and AQVX is the air quality viewing system. So I'm not sure that we sort of elucidated that at the start of the presentation. So I would suggest that anyone that's interested in contacting Karen or Fabian directly directly actually come through me rather than putting their email addresses. So it's deb.sparks@afac.com.au, and I can forward any inquiries on to Karen and Fabian. I don't think we've got any more questions for you. Have you got any final comments you'd like to put forward? Karen or Fabian, no final comments?
No.
Yeah, for us, it's really we would like to work with all the different sort of stakeholders, like all the fire and land management agencies, to ensure that the input data that we get is actually the most robust and most accurate. So we can actually then be sure that the forecasts that we're producing are the best forecasts that we can get. And yeah, as Karen mentioned, we currently rolling out the air quality visualization platform, and it would be great to get the feedback, because we really want to make sure that it's a system that's optimized for the stakeholders. So we sort of developing the science, but we're not the users. So it's really up to the people who use the system to ensure that it's working for them.
Yep, great.
Yeah, so with that, I'll just add to make sure that when you are looking at to think about how you would use it. So as you mentioned before, apiary sites, vignerons, even if you've got a fire going and you need to put a base camp and you don't want your firefighters in days of smoke. So there are multiple uses, transmission lines. There are things that we might not have thought of in developing the system. So feel free to get in contact to us to say, yes, you do want to see where all your local apiary sites are, if it's possible.
Great. Well, on that, I'll close off the webinar and say thank you very much to Fabian and Karen for their time today. And I'm looking forward to seeing this going national and plugging into all those other systems that are out there, AFDRS, Spark, whatever the future holds. It'd be great. So thank you, everybody.